Welcome everyone, my name is Konrad Kolesko, and in this short video I will talk about some limit theorems for general branching processes, and this is a solution to a problem that in its general form has been open for almost 40 years. The talk is based on the paper Asymptotic Fluctuation in Supercritical Kramp-Molyarios Processes, and it's a joint work with Alexander Iksanov and Matthias Meiners. So let us start. So as usual, we use the Harris-Ulam tree to enumerate the vertices. So what is Harris-Ulam tree? Is a tree whose vertices are sequences of the natural number of all length. So the root is the sequence of length 0, so it's the empty sequence. Then the first generation is constituted by the sequences of length 1, the second generation sequences of length 2, and so on and so forth. So for example, the first child of the sequence 1, 2 is the 1 to 1, the second child is 1 to 2, the third child is 1 to 3, and so on and so forth. Now for every vertex in the Harris-Ulam tree, we can take a copy of some random vector x with positive increments. We take an independent copy, and we use this x's to enumerate, to label the edges that leads to its offspring, to its children, and if there are no available x left, then we can put infinity. So we put infinity on such edge. And now we can define the S of u. The S of u is the sum. So for any u, we denote S of u as a sum over those labels on the path that leads to the root. So for example, we have S1 to 2 is the sum of those three x's. And the interpretation is that S of u is the birth time of an individual u. And the standing assumption is that the process is supercritical, meaning that the expectation of n is greater than 1, and this implies that the process survives with positive probability. And now we define the Kramp-Molyarios process. So the first ingredient is the S of u, the process that was defined on the previous slide. It can be seen as a branching random walk on R with positive increments, and by I we denote the individual that are ever born. The second ingredient is some Cadillac process phi. So for any so we are given some Cadillac process, and now for any u that are alive, we attach a copy phi of u. And the assumption is that the pairs x and phi for different u's are independent and of the same distribution. And now we can define a general branching process counted with characteristic phi, or in other words, the Kramp-Molyarios process, zt phi, as a sum over all alive particles. Then we take the corresponding Cadillac process phi, t minus s of u. T minus s of u, this is the age of the individual u at time t. So it also can be negative. And our aim is to find an asymptotic for the zt phi. So few examples. So the most natural is to take the indicator, and in such a way the Kramp-Molyarios process denote the number of individuals born up to time t. We can also count the number dead or alive particles up to time t, and also there are many other applications to biology, to random graph theory, or to computer science. And it turns out that the following function is quite important. So the moment generating function, which is defined for complex complex number, we take the expectation sum e2 minus z xi. And the standing assumption is the following, that there is some positive alpha such that the m of alpha is equal to 1, and it's called the Malthusian parameter, and the m of alpha half is finite. And the fact that m of alpha half is finite, it means that the consequence is that the function is well defined for z whose real part is at least alpha half. And it turns out that the solution to this equation m of z equal 1 are quite important. And on this picture I draw a few such roots. So one of the roots is the Malthusian parameter. Then there are other roots, and also if z is a root, then a conjugate is a root as well. And there might be some root on the critical line, and there also might be some root beyond the critical line, as on the picture, as long as the function is well defined on such domain. Now we need the following two sets, lambda and boundary of lambda. So lambda is the solution, it's the set of root on the right half plane, so right open half plane. So on the picture, we denote this root by blue color. Then by the boundary of lambda, we denote the roots on the critical line. So for us, the critical line is the line real part of z is equal to alpha half. And for the purpose of this talk, we assume that all roots from those two sets are simple. So the derivative m prime at such a root is non-zero. So now we can define few useful martingales. So by I of t, we denote the individuals that are born after time t, but whose parents was born before time t. So it's the first time in the generation that the particle is born after time t. And it turns out that the following process wt alpha is a sum over individual in this it e2 minus alpha s of u forms a martingale, and it's in the literature it's called Nerman's martingale. And it also can be easily checked that for any other root, the corresponding process, so we just replace alpha by other root, is a martingale as well. And why they are useful? Because of the following theorem. So in 1981, Nerman showed that the martingale Wt alpha converges almost surely to some limit. And under some additional assumption, if we rescale the process, the Crann-Moore-Yarges process, by e2 minus alpha t, alpha is the Malthusian parameter, then we have a convergence to some constant times this martingale limit, and the convergence is almost sure. And under additional assumption, the limit is non-degenerate, so it's positive on the survival set. So now, as we have convergence almost sure, we can ask whether there is some central limit type theorem, and it turns out that yes, but we have to subtract something more than just the term that appears in Nerman's theorem. So it's our result, our main result is so under some assumption on the x and on the phi, we can show that for any root that are on the right half plane, the martingale, the corresponding martingale is L2 bounded martingale, hence it's converged to some limit, and we can use this these martingale limits to to construct such a sum. So one of the root is the Malthusian parameter. So it's the leading term in such a sum. But there are more terms, subleading term, which we have to subtract from our process in order to get a limit, central limit type theorem. So then what do? We rescale it by e to minus alpha t half, and then in the case when there are no roots on the critical line, we have a convergence in distribution to randomly scaled normal distribution. And similar theorem holds when we have a root on the critical line, but the difference is that the normalizing factor differs. We have to divide by additional square root of t to see the convergence in distribution. So some similar results were already present in the literature. For example, Jansson and Neininger, who studied the limit theorem for fragmentation process. So they look at the second order in such process. Also similar result was proved by Jansson in 2018 for such a different. Here H is fixed, and Jansson was studying such a process. And also our recent paper with Alexander Iksanov and Matthias Meiner, where we studied the difference between martingale limit and the martingale itself. So the Nerman's martingale and its limit. So we studied the fluctuation, and can be seen also as a particular example of our theorem. That's all for this moment. Thank you for your attention, and see you in Mannheim soon. Goodbye.